Okay, so there was a question on graphing on 4.1, and I got a few questions over 4.1, and I think majority of the problem is interval notation and writing that out. I think Wiley tries to give you a hint. If they just say the interval, you're going to use a closed bracket in the case. You never use a closed bracket on infinity, but let's say this was minus 5 to infinity. I would write minus 5 to infinity in this bracket if it says the interval. If it says for concavity, a lot of times they want open interval. So if I need an open interval, let's say from minus infinity to minus 5, if there is a union, if there's two intervals in which my function's concave up on, then you have to write the correct notation there with the union. So then this could be something like 5 to infinity. I'm not saying this is the right answer. I'm just showing you how to input it correctly. A lot of students that emailed me just didn't write in the union, and they put that. So that is not, Wiley will not know how to input that, so they'll count that wrong. So that union, right there. If it says an open interval, use an open interval. If it says have an interval, you can go ahead and use the closed one. So that was just a comment real quick on that one. And then some students before class asked me how to go about graphing this. And it's not necessarily just the easiest thing to graph real quick. You have to do a lot of information to get to that point. So taking this function, first they ask us for inflection points in ascending order. So the inflection points are going to be when the second derivative equals 0, right? So I have, and I did this wrong. So let's look at this problem. I have 4x cubed minus 24x squared plus 12x. This is 4, 2, 13. This is 4.1 number 74 on 4.1. This is my function. Wrote it wrong again. I will get this. Okay. What do I have? I have x to the 4th minus 24x squared plus 12x. And then I'm only looking at points that are on the interval from minus 5 to 5, including minus 5 and 5. So taking the derivative, I get 4x cubed minus 48x plus 12. Setting this equal to 0 is going to give me maximum and minimums, but they didn't ask for that, so I might not have to do that. But I'm going to have to graph this. So here I get 12x squared minus 48. Set that equal to 0. So I have 12x squared equals 48. So I have x squared equals 4. So x equals plus or minus 2. So these are my inflection points of my graph. But I'm not asked to graph the function. I'm asked to graph the first derivative and the second derivative. Everyone should be able to graph the second derivative. This is a quadratic that opens up with y-intercept at minus 48, right? So if I come down to graphing this, it says graph the first and second derivative. I'm a quadratic that opens up, and my y-intercept is at minus 48. So I come down here, 40, 48. See if I can. You might need to zoom in a little bit to get this, depending on how touchy your computer is and your mouse is. So I need minus 48. So that would be the second derivative. Now I need to graph the first derivative, which is a cubic, so finding zeros of the first derivative tells me, finding zeros of the first derivative tells me where that crosses the x-axis at. And then I can do the first derivative test to see when the slope's positive and negative. When's the function above the x-axis and below it? So go back to here. So if I factor out a 4, this is a cubic, right? So using the rational root theorem, possible factors are going to be in the form the factors of 12 divided by the factors of 4. But if I factor out a 4, I have x cubed minus 12x plus 3. So when does that equal 0? So now the rational root theorem would tell me my factors are plus or minus 1, plus or minus a third. So does 1 doesn't work? Does 3 work? What would be 3 cubed? 27 minus 12 plus 3. It's 1/3 a factor. This is a cubic. So 27 minus 12. Let's test negative. That would be positive. So this would be minus 27 plus 12 plus 3 doesn't work. Are there any factors here?
When we were up in the tutoring center, Jerry had said that we should just use graphing utility.
Yeah. So, see, the factors are going to be in the form plus or minus 1, plus or minus 3. Does negative 1 work? Does negative 3? Or does 3 work? The rational factors. So, I'm only looking at minus 5 and 5. So, if I plug in minus 5, so if I look at the number line here, f prime of x, minus 5, 5. There could be factors in between here. So I'm only going to graph it here. But if I plug in minus 5, I get a positive number, right? Negative, wait, I get a negative number. I get a negative number. So that means my function is below the x-axis at minus 5, right? So then my derivative is below the x-axis. So my slope for my function is negative. But I'm not graphing my function, I'm graphing the derivative. So coming back here, I know that at minus 5, I have this function, or not this one, sorry, delete that one. I have to have this one. Minus 5, my function is above the x-axis. And then let's say on the other side, at 0 it's positive, right? If I plug in 0, my function is positive. So at 0, my function is 3. So really I have 0, 0, 3. Oh wait, it's not 3, it would be 0, 12. So I have really two options. If I put this at 0, 12.
How did you pick 12?
Well, if I plug in 0 to my derivative, I get 12, right?
Okay.
So the nice thing on this is it's either this function or it's this function, right? 0, 12. So I got to figure out which one it is. So if I plug in, they say, okay, estimate my points here. So I know rational root theorem. So the function, let's plug in minus 4, because minus 4 would be on these intervals, right? So, oops, where did that go? So if you plug in some points into the derivative, it's going to tell you if it's positive or negative. So if I plug in minus 4, what would I get? I would have a negative and a negative, so that's negative. So at minus 4, my function should be below the x-axis. So if I come back here, minus 4, the function should be below the x-axis. So that's this one, right? So this one would not work then. So this is, did I move that? Did move it. We need to be at 0, 12, right? 0. Zoom in a little bit. 0, 12. And if I plug in minus 4, it's below. If I plug in minus 2, the function should be above, the derivative should be above it, right? So if I come back here, plug in minus 2, I would have minus 8 plus 12 plus 3, so that's above the x-axis. So this one is going to be the only one that works there. Go back here, so the graph should be correct. And let's see, and overall it's going to be wrong because I didn't enter some things, but the graph is correct. Any other questions on Wiley assignments?
Can you do the second one on 4.2?
4-2.
Is that the crazy exponent?
Or no, that's the third one. Yeah, can you do the third one actually?
This one?
Yeah.
Fractions are not the end of the world, right? Okay, so let's look at this one. This is number 4.2, number 41. So 4.2, number 41. This one's actually easier than the one I did in class. The one I did in class when we had to factor out like a negative 1/5 or something. There's actually no factoring here. You're just solving. Hopefully, is that a 7 or a 2? 2 over 29, right? So I want to differentiate this and set it equal to 0 to find critical points. Critical points are points that are in the domain of the function where the derivative equals 0 or is undefined, right? So taking the derivative, I get 2 plus 2x to the minus 27 over 29. So I could rewrite this as 2 plus 2 over x to the 27 over 29. I want to set that equal to 0. So automatically, what's a critical point where this is undefined? X cannot equal 0. If it equals 0, it's undefined. So remember that first page I gave you the first week of class, Are You Ready for Calculus? A lot of that was solving for the values of x that satisfies when in a function equals 0. That's what you're doing here. Can find a common denominator. The denominator can never equal 0, so I need to find when the numerator equals 0, right? So this would be 2x to the 27 over 29 plus 2 equals 0. Basically, that would be the common denominator, right? So I want to solve when the numerator equals 0 because the denominator can never equal 0. So I'm solving for when does 2x to the 27 over 29 equal minus 2. So x to the 27 over 29 equals minus 1. What's the 29th root of negative 1 to the 27th power? Negative 1, right? So I can take this to the 29 over 27 and this to the 29 over 27, so I get x equals minus 1 to the 29 over 27, which x would equal minus 1 there. So minus 1 is a critical point. So if I plug in minus 1, the function exists everywhere. So if I look on the left side, if I plug in 0, and 0, right? 0 is also a critical point. I put that on the wrong side. Pretend I didn't do that. So let's say I plug in negative 5. So if I plug it into the derivative, negative 5 to a power is going to be a large number, right? So 2 plus 2 over a large number would be positive, right? So I'm adding, is it originally adding or subtracting? It's adding. So it's going to be a negative number, right? A negative number to the 27th power is negative. but it's going to be smaller than 2. So I take 2 minus something smaller than 2, I get a positive, right? If I take a half in here, minus a half, then if the half is in the denominator, that really becomes minus 2. So I take 2 plus minus 2 times 2, that's negative, right? And then the same thing here, plus. So I have a positive slope, a negative slope, and a positive slope. So this is a maximum, and this is a minimum, right? So the maximum, when I plug in minus 1, this would be negative, and this would be, oh, sorry, this would be positive, because I'm plugging into the function. This would be negative. So 29, so that would be 27 is the max at x equals minus 1, and 0 is the min at x equals 0. Trying the 27, I plugged negative 1 into the function. So negative 1 squared is positive 1. So 27 minus 2 would be, sorry, 29 minus 2 is 27. So then I have the minimum is 0. That happens at x equals 0. The maximum is 27, and that happens at x equals minus 1. All right, so today we're going to talk about maximum and minimum problems in application. So this is going to be 4.5. It's applied maximum and minimum problems. So we're going to look at optimizations problems. And the first two we're going to look at, you've done, more than likely you've done in college algebra at some point in time. And I probably am not going to take the time, well, I'll write them up. So let's look at the garden problem. Say you have 100 feet of wire. And you want to maximize the area that you can, maximize the area of your garden. All right, so I have some garden. Let's call this X and this Y. And I can only have 100 feet of wire. What is going to be my length of my garden, and what's going to be the width of my garden? That's going to give me maximum area. Does anyone have any intuition from college algebra? That's going to be a square, right? So given a set perimeter, your maximum area is always going to be when you have a square. Like if I can make a rectangular into a square, it's going to increase the area given a set perimeter. But let's go through and show the calculus here. So on these types of problems, your first kind of instinct is to draw a picture. From the picture, you need to find an equation in one variable. So you're always given some information to write an equation, and then write an equation in terms of the function you want to maximize and minimize, right? I want to maximize the area. So what would be the area of this garden? XY, right? Because I don't really know what's going to be a square at this point. It could be a rectangle. So I need to write X and Y in terms of either X or a Y so I can get a function of one variable. So what's another function I could write that involves X and Y? In the perimeter, right? Exactly what I needed there. So here I have 2X plus 2Y is 100. The X I pick and the Y I pick have to satisfy this equation. But if I know one, I automatically know the other, right? If my X is 10, then my Y is going to have to be 40, right? Because I have 100 feet. So I can solve for one in terms of the other from this equation. So let's say go ahead and solve for y. Y would be 100 minus 2x over 2. So that's going to be 50 minus x. So if I plug this y, in terms of y here, I have the area is x times 50 minus x. So I've gotten my area function in one variable. Now I can differentiate, set that equal to 0, and find my critical points. So I'm going to write this as a equals 50x minus x squared.
So if we thought you get 2x plus 2y.
How did I get 2x plus 2y? Because the formula for perimeter would be x plus y plus x plus y. So that's 2x plus 2y. So what are my bounds on x? I can't have x go to infinity because I only have 100 feet of wire. So x could be 0, but it really wouldn't make sense. But that's fine. It could be 0. Then I have a 0 area. And what's the maximum x can be? 100? 50. It can only be 50, right? Because I have two x's. Right? So if I just make, that's just a line. So if I have an x here, I have to have an x here. So it turns out it's 50. So I want to keep that in mind when I differentiate it. The critical point has to be on this interval, or it doesn't make sense. So now differentiating a, I get 50 minus 2x equals 0. So then I have 2x equals 50, so I have x equals 25. Well, if x equals 25, then y equals 25, right? So it turns out maximum area is when x and y is 25. So the area, the max area is when x equals 25 feet and y equals 25 feet. And the area would be 25 times 25.
Why is y the same as x? Because it can only go to 50.
Y is the same as x?
Why?
Well, so x is 25. So I could plug this x into this equation and solve for y. Right? Because y is 50 minus x. And once I find x, I plug it in to find y. These types of problems, you're always going to have a procedure. And the procedure, so let's look at the procedure real quick. So first thing you're going to do is draw a picture. I know it's kind of silly, but you'll get partial credit for throwing a picture. If it's talking about a cone, throw up a cone up there. At least you read the question type thing. But it's going to help lead you to your relationship. And you're always going to end up with two relationships. One that will be given, like a perimeter or area or volume or surface area. And then one that you want to maximize or minimize. So from the picture, you're going to write out your formulas. And then step 3 is the crucial point. The function in one variable. So your formula or formulas are going to allow you to solve for one variable in one formula, plug that in for that variable in the formula you want to maximize or minimize, and then differentiate with that one variable. Because you can't differentiate a function of two variables. You'll get a related rates, which won't make sense for a maximizing or minimizing problem. And then step 4, you want to also keep in mind the interval. The function has to make sense within a certain bound. And then step 5 is to actually find the maximum or minimum.
And in this case, that was the 625.
625, and this would be feet squared, right? So if I have cattle or something, and I only have X amount of fence, then I might need to maximize the area I could fence them off, and then that will tell me how many cattle I can buy, because so many cows means so many feet squared per cattle or something. So these problems can get a little bit more involved. I could also say I have 100 head of cattle. I have to make sure I have a given amount of acres. So I want to minimize the perimeter because I want to minimize how much fence I have to buy. So it's along the same lines, right? I need to get a formula for perimeter given a set area. Question?
So how do you know x equals 25 is the max and not the min?
So from here, that's a very good point. Very good point. So I can look here, I have a quadratic that opens down. So I know that whatever I get is going to be a maximum point. However, I need to write something like that. And really, you get it from testing your points. If I take the area at 0, I get 0. If I take the area at 25, I get 625. And if I take the area at 50, I get 0, right? Because this would be a closed interval. So when you have a closed interval, you test your endpoints and your critical point. So here, this would tell me this is a max. And the minimum would be 0. Or you can kind of graph this as a quadratic that opens down. So this point is going to be the maximum of a quadratic that opens down. Or you could do the second derivative test. What is the second derivative here? Minus 2. Minus 2 is negative. So that means I'm concave down, and concave down would be a maximum. But you do need to kind of pay some lip service to that. You can do it by testing, or you can test a double prime of x equals minus 2, which is less than 0, so I'm concave down, so I have a maximum. But you do want to go about that, because sometimes you forget the applications. Like, okay, maximize it, the critical point is going to get a maximum. Minimize it, the critical point is going to be a minimum. You want to do one step further, either test the endpoints or do the second derivative test. And the second derivative will verify it's a maximum. All right, so let's look at a little bit more complicated type examples. The next one you probably did in college algebra as well. So if I'm given a piece of sheet metal and I want to find the largest volume I can make, and let's say this sheet metal is 30 inches by 16 inches, and I'm going to come in here and I'm going to machine away the corners, and when I'm machining away the corners, I'm going to be able to fold this up into a box. Right? So my drawing's not necessarily the best. This one's in your book. Right? So I have a piece of sheet metal that's 30 by 16 inches. If I come in here and I cut out the corners a distance of x, and I fold this up, I have a container, a rectangular container, right? And I want to cut out a magic number x so that it maximizes the volume, right? So let's say this is x here. So what is the volume of a rectangular container? Very good. Length times width times height. So I want to get length, width, and height all of a function of x, because that's my only variable, right? I'm just going to come in here and cut out a distance of x on each corner. So what is my length going to be? The length of my box. What is it going to be?
2x.
30 minus 2x, right? 30 minus 2x. What is my width?
16 minus 2x.
Very good. And what is my height?
X.
X, right? Because I flip up the flap that's left here, and that's the distance of x. So my volume is going to be 30 minus 2x, 16 minus 2x times x. What are my bounds on x? X could be 0, sure. I'd have 0 volume, but it could be 0. What's the maximum it could be? 8, right? Because if I come in here and cut 8 here and 8 here, I don't have any width left. So the maximum can be is 8. So when I want to test my critical points, I can test 0, a critical point, and 8 to see if it's going to be maximum or minimum. Or I can do the second derivative test, either way. So go ahead and write out volume. If I FOIL all this, I get 4x cubed minus 92x squared plus 480x. So if I differentiate that, I get 12x squared minus 184x plus 148. When does that equal 0? This is a quadratic. I could factor out 12. And factor again, I could do the quadratic formula. Turns out x is 10 over 3 or x equals 12. Can x equals 12? No, so that's not in our interval, right? So I can test my points because on a closed interval, if I plug in 0 for x for volume, this is my volume function, right? If I plug in 10 over 3 or if I plug in 8, I get 0 here, 0 here, and I get 726 here. So it turns out my maximum volume is 726 inches cubed. And this happens when x is 10 over 3 inches. Can you guys see this is kind of the same things? In the beginning, you have to find your own function to maximize. Once you have that, it's just 4.4, maximizing that function. Finding the derivative set that equals 0 and solving for critical points and then testing your endpoints. Question?
So do you always plug it into the original equation? You don't
To test,
yeah,
you
don't
plug it into
the derivative?
You don't plug it into the derivative. No, you plug it into the velocity, the original function. So, or velocity, sorry. This is the volume. So what is the volume at 0, when x is 0? Volume is a function of x. If I know x, I automatically can find the volume by plugging it in this function. Right? Generally, when you write equations, if you have a set perimeter, you can find the volume. Like if I give you a can problem, if I have a set volume, you know the surface area given the height or the radius, given two variables. Two equations, two unknowns. You know one variable, you automatically know the other one, right? So let's look at an example where we have let's say I have a can that holds 1 liter. And let's say I'm selling whatever I'm selling in this can, and I'm selling 1 liter at a time. And I go to a manufacturing plant, I said, what do I need? I'm going to make my can out of a certain material, and I want to know how much material I'll need per can. So, and I want to minimize that. So I say, how tall should my can be, and what the radius my can should be to minimize the surface area for a given volume of 1 liter. Does anyone have an idea of the relationship between the radius and the height of a can to minimize surface area? Well, it's formula, but it turns out the radius and height, there's a certain relationship that's always going to be minimizing the surface area. When your can is a certain ratio of your radius, you have a minimum surface area. So let's go through it and find that. So what is going to be the volume of a cylinder? Area of the base times height, right? What is the area of the base? Pi r squared times the height, right? Pretty straightforward there. What is the surface area formula? Area of the top plus the area of the bottom plus the area of the side, right? So what's the area of the top? Pi r squared, right? The area of a circle is pi r squared. And the area of the bottom is also pi r squared. So I have pi r squared plus pi r squared. So this is the top. This is the bottom. What is going to be the area of the lateral surface? It's going to be the circumference of a circle, right, times the height. Because if I make a can here, so you guys know how to find the area of a rectangle, right? Length times height. Length times height. Times width, whatever you call it now. So now if I put this into a circle, this length is the circumference of a circle, right? Times the height. So what is the circumference of a circle? 2 pi r times h. So the surface area can be written as 2 pi r squared plus 2 pi r h. So in this problem, I want to minimize the surface area given that the volume is 1,000 centimeters cubed, which is 1 liter. Minimize, I don't know where that R came from. Minimizer? I don't know.
The other one, area, surface area.
Surface area. Let's leave off the last letter. Okay. So I have pi r squared times h is 1,000. Right? This is my formula that I can solve for h or r for to plug that in for surface area. Which one's going to be a little bit easier? H, right? If I solve for h in terms of r and I plug h in, I only have to plug it in one place and it's not squared. If I solve for r in terms of h, I have to plug it in twice and it's squared in one of those places. So naturally, if I solve for h, I get 1,000 over pi r squared. So now I use that h for the surface area. I have 2 pi r squared plus 2 pi r times h in terms of r, which is 1,000 over pi r squared. Does everyone follow me to that step? Really, that's the hard part. Because now it's 4.4, which is differentiating, setting equals 0, find the critical points, and testing that. What are my intervals here? Can the radius be 0 and have any volume? In this case, it cannot be 0 because I need to have a can that has at least 1 liter. My radius can be really, really, really small. That means my can has to be super large for the volume to be 1 liter. So this is an open interval. R has to be greater than 0, but less than 1,000, a million. It just depends on how small R is, right? So this is an example of an open interval. So if I find a critical point, I can't test endpoints. I have to do the second derivative test or the first derivative test to see the concavity on the interval. So let's clean up the surface area equation. 2 pi r squared plus the pi cancels, the r cancels with one of the r, and I have 2,000 r, right? So automatically I know r cannot be 0, because then it wouldn't make sense. It's undefined. The function for surface area is undefined at 0. So r cannot be 0. So I have an open interval. Now I need to differentiate this. What's the derivative of surface area? Well, that's going to be 4 pi r minus 2,000 over r squared. Set that equal to 0. Find a common denominator. I get 4 pi r cubed minus 2,000 over r squared equals 0. So the denominator can never equal 0, so the numerator has to equal 0. So it is 1 is 4 pi r cubed minus 2,000 equal 0. When 4 pi r cubed equals 2,000, divide both sides by 4 pi, and I get r equals the cube root of 2,000 over 4 pi, which would equal the cube root of 1,000 over 2 pi, which would be 10 over the cube root of 2 pi. Right?
Excuse me, do you neglect the r square in the denominator?
Here? Well, the denominator can never equal 0. Right? So if I have 0 over 5, that still equals 0.
Yeah.
So yeah, you can just kind of ignore it. You could also say, let's multiply through by r squared. Right? So then I get r, the r squareds would cancel, and 0 times r squared is r squared. And I can do that because r does not equal 0. You can only multiply through by a variable when that variable does not equal 0. If that variable could possibly equal 0, you cannot do that. Make sense?
So on a test, we put that in our calculator and then.
You could just leave it at this. If you put it in your calculator, that's fine. On the test, your numbers will be a little nicer.
Okay.
So we have r, and recall that we have this formula. H is 1,000 pi r squared. So if I want to solve for h, I have 1,000 over pi 10 over the cube root of 2 pi squared. So if I go through and simplify, it turns out I get 20 over the cube root of 2 pi. So it turns out to minimize surface area, your can's height is twice its radius. So if you have a can that has a radius of 5 inches, the height of the can is going to be 10 inches to minimize that surface area. This case, our numbers didn't come out nice, but they could come out a little bit nicer. Question?
How'd you simplify the 20 over cube root of 2 pi?
See what we end up with here. So I have 1,000, I have pi, I have 100, I have 2 pi to the 2/3. So that would end up being, let's see what I want to do to get it in that formula. So flip and multiply. So really I have 1,000 over 1 times 2 pi to the 2/3 over 100 times pi. So what would I get here? This would cancel, and I would have 10 times 2 pi to the 2/3 over pi. And I multiply top and bottom by 2 pi to the 1/3.
You could
Yeah.
pi to the -1 and just subtract this stuff.
Yeah. So I would also have this 2. So I wanted to look just like this. So if I multiply top and bottom by what I have here, so I purposely wrote it like this because it looks exactly like 2r. So at this point, I have 2 pi, all that to the 2/3. So if I multiply by 2 pi to the 1/3 on top and bottom, what would I have? I would have 2 pi to the first power, right? Times 10. So the pi is going to cancel. So here I'd have 20 pi over pi to the cube root of 2 pi. And the pi's cancel. So I get exactly this. It's, from here, this simplifies and it looks exactly like 2r. But if you simplified it here, you would be fine. It just doesn't look like 2r, right? But it is exactly 2r. It's just not in that form. Algebra. It's your best friend.
Right. Okay, the R is then.
The R is this. Once I find this, I plug it in this equation, and I wasn't necessarily expecting you guys to make this leap in your head, but you can, now that you've seen it, I didn't do anything illegal, this is exactly 2R.
Why is the cubic root like cancels, like becomes just square root? The
When you have like-based, I'm not sure,
I mean the last one. The answer.
that should be cubed anyway. Sorry, let me fix that. Here?
I mean the answer.
Where your
This?
pi is canceled, the 3 is marked out.
Oh, sorry. Yeah, the 3 is still there. The pi just cancels. But it's just making it look just like 2R, so you can see that. Okay, so the problems can definitely get more complicated.
More than this.
So let's look at example number 4 in your book. We're not going to have time to probably finish this one. So let's say we want to find the radius and height of the right circular cylinder of largest volume that can be inscribed in a right circular cone with radius 6 inches and height 10 inches. And you can see why a picture is your friend. You guys know what inscribed means? So I have a right circular cone.
I didn't even know what that was.
A right circular cone, and I'm going to inscribe a circular cylinder with largest volume. So a circular cylinder is going to come in here, and it's going to be inscribed so I want to find the radius and height of the magic circular cylinder that's going to maximize the volume that's totally inscribed within this right circular cone. The right circular cone has a height of 10 inches and a radius of 6 inches. So geometry, right? So the first thing we kind of want to see what's going on here is the largest volume. What is the volume of a cone? Or sorry, volume of a cylinder. Because that's what I want to find. The right circular cylinder of largest volume. So the volume of a cylinder, right, we've seen this one, pi r squared times the h. So I have two variables. I have an h and an r. Do I know the volume of a right circular cone? I can find the volume, right, given this, but that's not going to necessarily, I have to relate the height of the cone to the height of a cylinder that's given here. So let me see if I can take this out. So this is going to be the height, right? It could go all the way to the top. So I'm going to move that here. And this would be the radius. So I'm going to see if I can draw that over here. Right? This would be maximum to be 6, right? And this is going to be the radius of the cone. This has a maximum to be 10, and this is going to be the height of the cone. Can you kind of see that? All right, if I take just this and I make a cone out of that. The maximum h can be is 10, and the maximum r can be is 6. So I kind of have an interval for h or r, but I want to get it all in a function of h or all in a function of r. So what you're really going to do here is similar triangles. So this would be r here. This would be 6. So I can say 10 is to 6 as h is to r. 10 is to 6 as h is to r. Oh, it wouldn't be 10. It would be 10 minus h. Okay, wait. Let me go back. 10 is to 6, or 10 minus h. 10 minus h is to r, as 10 is to 6. So we're going to run out of time. We've already done. We'll finish this problem tomorrow, and we'll look at some Wiley problems and kind of see. Experience is your best bet on these. If you know what a right circular cone is, you can begin to start the problem. If you don't, you have no hope. So experience, I mean, honestly, you have no hope. So hopefully I can show you quite a bit more of these, and then also show you ones that have come up on final exams.